I think we are recording. Yeah, okay. Um, all right. So we'll begin this, I guess, the fourth lecture of the course ISSS and ISSS, generative modeling using VAs. So we'll do a quick recap of what we had done last class, right? So first thing is we spoke in a bit more detail about what the genetic modeling problem statement is, and a brief recap is that, let's say we have some samples from an unknown distribution. What we want to do at the end of the day is be able to generate more samples which are like the samples that we have at hand. A simple example could be, let's say you have examples, images of dogs. You want to generate more images of dogs, right? Based on whatever samples you have. And then we looked at, this idea of GMMs as a in prerequisite, and that was because so we had introduced Gaussian mixture models under the thought process of trying to understand what a latent variable formulation means, right? And in one of the examples that we discussed here, we saw that if I take the latent variable to be the type of the image that I have, for example, if I have only images of dogs and cats, right? So if I use a K, for example, to understand, so if I use two Gaussian, distributions and their mixture to model these two different types of images, I could basically, have the latent variable to be the type of the image, that is either a dog or a cat, and that was in some way relevant for us, right? So we'll talk a bit more probably today about what relevance of this latent variable means, and we also spoke about the most trivial latent variable, that being the data, the variable x itself, right? And we also spoke about this manifold hypothesis and what uh, probable implications it could have in our analysis. Um, then we spoke about this variational inference, a basic idea, a basic technique that exists in this field. What is inference and what is variational inference? And then we motivated this to, and we went to this VAE formulation, where we spoke about we did one part of it, that is we looked at the latence formulation, and where we have some latent called Z, and we are looking at it's so the model likelihood can be seen as a marginal over the latents. And then we introduce this distribution called Q distribution, and that turned out, we assume it to be a multivariate normal distribution, and we saw that we can then look at a term called as f theta of Q of Z given X as a lower bound on the actual model log likelihood, right? And then we said that we want to maximize this lower bound because that would end up maximizing the log likelihood of the data. And that is required because we want to minimize the KL divergence between the true distribution and the model distribution, right? Um, then we saw how much off is this lower bound from the real value, and that came out to be some sort of a KL divergence between the two terms, which are the approximate latent posterior and the model latent posterior, right? And this is where we saw the variational inference connect, right? Basically, we want to make this approximation that we have as close as possible to the model latent posterior, which we are not able to have a tractable value. So we have this sort of approximation for it. Okay. Last class, I mean, we spoke about this, but I guess we can try proving this. So I left this as an exercise, the idea that, let's say if I have a Gaussian mixture model, how can we prove that the integral of that Gaussian mixture model, is that a valid PDF or not? To prove a valid PDF, two things should be true. That is basically, it should be non-negative. Sorry, it should be non-negative. That it can be zero or positive throughout, and the fact that it should integrate to one. Um, so any thoughts? How would you go about proving proving these two conditions?
Yeah.
We'll take a look.
So
Hmm.
I think given that it's a summation of Gaussians,
Hmm.
and Gaussians have infinite support and have probability always greater than zero.
Right,
So this mixture model also will have probability greater than zero for the entire support. That is the
right.
first thing.
Hmm.
Secondly, given that uh, these pi k's or the weightage given to each Gaussian also sums to one, and
Hmm.
given that uh, the area under each Gaussian is equal to one, therefore the summation of Gaussians will also equal to one.
Right. Yes, makes sense.
So
Hmm.
apart from this, is there any way to prove this, or is this logic enough?
Yeah, no, so we can prove it through and through mathematically, but yes, there'll be some here and there, some tweaks that we'll need to consider. So let's discuss that, right? So first thing, yes. So the thing is that each Gaussian is, as we know, it's has non-negative support overall. I mean, its support is the whole real space, RD space. So yes, it's going to be a non-negative value for each x, right? And given the fact that pi k are all greater than 0, right? So this with the fact that pi k are all greater than 0, so you will never have any element. So there doesn't exist any element x such that p theta of x will be less than 0, right? This is the first part, right? Second part is simple integration, but there is one small thing that we need to just keep in mind. So let's say sigma k pi k. So this is what we have. This is what we want to integrate, evaluate. So now, generally, this integral and summations cannot be interchanged, right? There are only special conditions where they can be interchanged. So now, why is that, right? So let's say we'll take a simple example to motivate what I'm saying. So let's say, for example, um, I have a function, let's say f1 of x is simple, let's say x or x squared. F2 of x is, let's say, minus x squared, right? Now I want to integrate, I want to find out this integral. Now, as we know, the support is, overall real numbers. Um, f1 of x plus f2 of x, right? Let's say I want to do this. So what are we saying from this? One way of thinking is that this can be written as like this, right? Um, f2 of x. Now, as we know that, if you evaluate these two, so this one is going to come out to be x cube by 3, but from infinity to minus infinity. So this is going to be just infinity for that matter, right? So some infinity and plus again some other infinity, or basically, yeah, minus infinity. But again, these two are not. So this operation as such, infinity minus infinity, is not defined, right? Whereas this integral is going to give me just 0, right? So are these two equal? We don't know. We cannot say because this operation is not defined. So generally speaking, you cannot just look at you cannot just exchange summations with integral symbols. So there are some theorems which we need to understand. But here, under a special case of that theorem itself, the idea being that this quantity is always positive. If that's the case, then this sort of so we can always exchange these two operations. So this leads us to this idea. So I will have over Rd pi k n mu k sigma k. Now this is over x, so pi k is a constant, and then I can just this becomes trivial, so I can just write sigma k pi k. This integral becomes 1, and this we know from the statement is 1. So therefore, this p theta of x integral is equal to 1. Therefore, it's a valid PDF. So this is the I mean the proper mathematical way of going about it. So and this interchanging of summations, integrals, this is all I mean it requires proper thought process to exchange. Only case where you don't need to think about it at all is when you have two summations which are both again finite in nature, right? If I have two summations, for example, going from some finite set, right, and another finite set of anything here, then I can go ahead and exchange them without any thought process. Otherwise, there are conditions you need to fulfill to make sure that these two are exchangeable, and then things become a bit more clear. I mean, easy to solve. Is this clear?
Yeah, this is clear.
Okay, good enough. So this is done. So okay, so we'll now move on to this, the part two of this VAE formulation. So last where we left was basically this idea that we have a term called elbow, evidence lower bound, and we said that we want to maximize this quantity. But what we have done till now is we have just given it a nice name and moved on. So now we'll dissect the elbow in more detail. So again, from last class that we had, so we defined elbow, that is f theta of q of z given x, as this quantity that is expectation over qz given x log p theta of x comma z by q of z given x. And we also discussed that the random variable here is z. And for now, what we're taking x to be a known quantity, right? Something known. That is, I want to find out this so-called lower bound for a given x, right? And then simple algebra shows us now this we can write it as p theta of x given z into p theta of z. This is by conditional probability definition, right? And then we'll split this log into two components. One is log of p theta of x given z plus, and then this whole part into another part here. And this becomes the first part. And the second part is just a KL divergence between Q of z given x and P theta of z. So one thing you need to remember is that previously what KL we saw was between the approximate latent posterior and the model latent posterior, right? Here the KL is between the approximate latent posterior, right? Approximate latent posterior and the model prior, right? This is prior because from this sort of definition that we have for when we split this joint distribution into conditional and marginal, right? Okay, so one simple question: what is the so we said maximize f theta of q of z given x. What are we maximizing over? What are the parameters of this maximization? Any thoughts on that?
Uh, in the sense,
Right. So for example, what are the factors that you need to change so that you will maximize f theta of z given x? So what is the argument of maximization here?
okay, over theta,
Over theta and
and okay, I can't think of anything else actually.
so yes, okay. So here we have two things that you want to maximize of. One is theta and one is q of z given x also, right?
Hmm.
Um, So because as you can see, so previously we saw that so log p theta of x, yes, depends on theta. That is true. So but the idea is that we want to maximize this elbow, and q is also a function here, right? So we want to change q such that this lower bound becomes as good a lower bound. I mean as much close to p
Hmm.
theta as possible, right? So
Right.
that also a parameter that we want to maximize over. Now, a small aside. So this sort of maximization, I mean, this sort of problems are basically a part of something called as variational calculus. So the idea here um, calculus. So here the idea is f theta of q of z given x. So this is called a functional, because this is a function of a function and we want to
Okay.
maximize over that function, right?
Understood.
Hmm. So q of z given x is also a function, as we know, because this is just going to be it is going to take a random variable z and map it to, let's say, some real number, a positive real number. Let's, yeah, to be more precise. So yeah, so this is called a functional. So you might see some literature sometimes, okay, saying this is something called a function. So that's what it means. So it's a
Hmm.
function of a function, and the internal function that we have, we want to maximize over that also. So basically, the idea is that for a given x, we want to keep changing this q distribution such that f theta of qz given x increases, which will then increase the model log likelihood, right?
Okay. So,
Hmm.
uh, so changing Q means like changing the dimensionality of Z, etc., etc.
No, no. See, so let's say, yeah. So what does changing q mean, right? So let's see that. So, um, changing q. So see, z is a random variable. Already we know, right? Or random vector. So
Right.
its dimensions are fixed, right?
Sorry,
So it's
sorry.
a sorry.
Could you please repeat? You are saying like Z is a random variable, and then what else did you say? Oh,
So
it has fixed dimensions.
fixed dimensions, right? So it's a
Okay.
random variable or a random vector for that matter. But yeah, it has fixed dimensions. So we
Okay.
don't change the dimensions. So what the idea here is, this q of z given x could either be, let's say, a Gaussian, could be exponential, right? Or could be Gaussian with changing parameters and so on. That is what we want to change.
Okay. Okay. Understood. Yeah.
Either the form can change, or you can have the same form, but the parameters
Parameters.
of the form can also change.
Yeah. Yeah. Hmm.
So these two
Right.
things are possible, right? So this is
Right.
the idea of yeah. So this is how Q will change, which will change this one. Clear?
Yeah. Yeah. Thanks.
Right. Huh. So now we'll go ahead and introduce neural networks, because again, the idea is now. So the question then, a very quick question, because now we have this idea that, okay, I can change the form also, I can change the parameters also. So what do I do? How do I change that such that, and with again the idea that, okay, can we use back propagation? Because ideally this whole thing needs to tie up with neural networks. We want to use neural networks to approximate the function, which takes, let's say, any sample from a uniform distribution to my the real unknown distribution called px, right? So for that, what the authors of VAE did was that they can model now the p theta of x given z as a neural network with parameters theta. And now what they go ahead and do is they model q of z given x as a neural network with parameters phi, right? So changing q would basically imply that I have to change phi, as you already discussed, right? So any distributions parameters, if it is there, so changing the distribution means changing its parameters. So basically, now we will have two sets of parameters, and we want to maximize over theta and phi, because we already said that we want to maximize over theta and q. Now q has been parameterized using this parameter set, let's say theta, sorry, phi. So therefore, we want to maximize over theta and phi, which are again parameters of two neural networks. So again, if I want to update any parameter in neural network, I need to compute gradients with respect to those parameters. So I need to be able to do this particular operation, right? That is, I want to maximize f theta of q phi of z given x. Notice the phi now, and the expectation will be over this q phi, which is my approximate posterior now, and of the model likelihood, and the KL divergence is now between q phi of z given x and p theta of z, right? So everywhere q becomes q phi, because now we are parameterizing q with q phi. So this is the first statement. This is the first thing that is changing. Next is let's come to some assumptions which the VAE authors took to operationalize this whole maximization procedure. So the first assumption that they have taken is that they model this p theta of z as a Gaussian distribution, multivariate Gaussian distribution with mean 0 and variance covariance matrix to be I, right? So that is the model latent prior is isotropic Gaussian. Isotropic Gaussian basically means this n0 I. And very clearly we can see that this does not depend on theta at all, right? Because for a multivariate Gaussian, I just have two parameters, mean and the variance covariance matrix. Here mean is fixed, variance covariance matrix is fixed. So this doesn't depend on theta at all. So I can just write p theta of z as p of z, some prior over the latent, right? Which is n0, z of 0 comma I. This is the first assumption. Second assumption is that we also assume q phi of z given x as a Gaussian and of this form, that is basically q phi of z given x can be seen as a Gaussian distribution over the random variable z, but with mean as mu phi of z given x and the variance covariance matrix coming to be sigma phi of x, right? So if you see here, we now have your mean depending on x and phi, variance also depending on x and phi. So therefore, if phi changes or if x changes, q phi of z given x changes, which is exactly what we want. So we want this q distribution to be a function of x and depend on phi also, which is exactly characterized in this form. So then, so here the idea is that so your mu phi of x is basically the mean parameter of this Gaussian distribution. So any idea what these dimensions should be? What dimensions of mu phi of x should be?
So same as dimensions of Z.
Same as dimensions of z, right? So
Yeah.
dimension of z. Let's take it for now. Let's say r. We'll see if we have some notational issues. And the other assumption, part of this second assumption itself, is that they've chosen to take sigma phi of x as a diagonal matrix. Right now, what that means is that, I mean, as you know, that all the non-diagonal elements are zeros. We'll come to what the implication for this is going to be. And the fact that we want the diagonals to be strictly positive. So can you think of why the diagonals should be strictly positive in a variance covariance matrix?
So that lambda is greater. So that eigenvalues are greater than 0. Therefore, the matrix is invertible.
Right. So yes, so two thought process here. So one is yes, you'll have an invertible matrix. So this is a point, like having this assumption eases up a lot of thought processes here. So one is you'll have invertible matrix, yes, correct. Other thing is you'll have a PD matrix, right? Strictly positive, I
Yeah.
mean,
Yeah.
positive matrix. And third, again, operationally also you need to be strictly positive because the diagonal elements of a variance covariance matrix represents variances.
Oh,
So
right. Correct.
always or negative. Right? But here in this case, we need to be strictly positive because of the fact that we want an invertible matrix. So this is generally true, but we want greater than 0, right?
Yeah.
Now, again, so then what are the dimensions of, it's a diagonal matrix. So how many values do we want from the neural network?
So R, same as dimensions of Z.
Right? Again, R,
Yeah.
because all the other elements are zeros.
0.
So now a simple question. So how do we get strictly positive values output as output from a neural network? What could be one function that we have discussed, by the way, in classes, that this function gives always strictly positive values?
Okay. So you're saying like from neural network means from the last layer of neural network, or are
Right.
you saying like which? Okay. So we can
Uh,
either use softmax or we can use ReLU. We can use
okay.
many such things.
What? One second, one second. So I've got softmax.
Softmax, yeah.
ReLU, yeah.
ReLU.
What else? Any other thoughts? So, okay, can we actually use ReLU though? What do we want?
Okay, we want strictly positive, so we can't use ReLU. Correct.
ReLU,
We can't
right?
use ReLU. Yeah.
Zero. Right. Okay. So ReLU is out. Softmax, do we want to use softmax, by the way? It is strictly, I mean, it is positive. It can give zero, not a problem. Okay, let's assume that it'll give zero. It'll not, it'll give strictly positive. But still, do we want to use softmax? There are some issues which will come with softmax, though, right?
Yeah, yeah. The summation will be equal to 1,
Right.
which is
So for example, let's say if I mean, having that constraint over the variances doesn't make any sort of, sense here, right?
yeah, yeah.
Oh, right. So this is also out. So okay. So how did we say that the Gaussian distribution has an infinite support? What was the thought process there?
Because
Why?
it's defined at every value of x in this space.
Right. But I mean, operationally, mathematically, we said that okay,
And the probability is greater than 0.
probability is greater than zero. Why? What term in the whole Gaussian distribution gives us a compulsory thought? I mean, short way of saying
because
that
it's
okay, positive.
because it's exponential raised to power x
Exponential.
square.
Right. That's
Right.
it. So that's the idea. So here, I can use an exponential function on at the output layer of the neural network to make sure that I always get a strictly positive value,
Okay. Hmm.
right? Because exponential, again, as we said, the exponential becomes zero only if x is minus infinity.
Infinity. Yeah.
Right? So and I mean we'll make sure that we don't reach minus infinity, but
Hmm.
yes, that's the thought process. So basically, the idea being that your x is taken as an input to the network. Let's say we'll define a network by parameters called phi, and this network is going to spit out two values. One is sigma mu phi of x and sigma phi of x, right?
Right.
So here x basically is going to be an element in RD space. Mu phi of x is going to be an element in R space. Sigma phi of x is going to be an element in again in R space, because remembering everything else is zero. And then what we can do is you want okay, actually we'll come to that later. Okay, so this is the idea, right? So you have a neural network which takes in x as the input, outputs two values, mu phi, sigma phi, which depend on x, which depend on phi. So therefore, q phi of z given x can be basically brought into existence at the end of the day, right? Using an x. Okay, so we'll take a small detour and talk about this multivariate Gaussian distribution a bit, and then come back to this idea of what non-diagonal zeros, what implication do they have, and this will be at two levels. One is again operationally, how does it help and etc. And then what implication it has over the latent variable, right? Um, and then we'll discuss some more terms in this elbow. Okay, so any doubts till now?
No, no.
Good. So we'll move to multivariate Gaussian distribution. So again, let's recall the distribution. So first thing was that if I have a univariate Gaussian distribution, I can look at the PDF of that in this form. And if I have a multivariate distribution, it's defined in this form such that sigma has to be invertible so that sigma inverse can exist, and it has infinite support. Now, the idea is that first thing is that some properties of sigma. First is it's symmetric, and this is from the fact that it is a variance covariance matrix, right? So what ends up happening is that so every element of the sigma ij is just the covariance between xi and xj, right? And covariance as a measure is itself symmetric. I mean, as a quantity is symmetric. So therefore, sigma ij will be equal to sigma ji. So this is going to be a symmetric matrix. And moreover, it is going to be actually speaking, any variance covariance matrix. So any variance covariance matrix is actually a PSD matrix, right? So this you can see from the fact that the way you would be define sigma, this is basically an expectation over, let's say, the random variable x, and we say it's x minus mu into x minus mu transpose, right? So if you take, let's say, some vector, let's say a transpose sigma a will turn out to be greater than or equal to 0. So this you can, try to prove it. Leave it as an exercise for now, and we'll do it in the next class. Now, for our case, we will assume it to be invertible also, because again, if it's not invertible, this quantity will basically not exist. And what will end up happening is it'll become something called a degenerate multivariate Gaussian distribution, which has basically no use for us. So for now, we'll say that sigma is a positive definite matrix, right? So all of its eigenvalues are non-negative, positive, and therefore it becomes invertible. All right. Now we'll talk about some properties of this multivariate distribution. Before that, we'll uh, take a small aside on this, something called as moment generating functions. Now,
So one question here.
yeah, yeah.
So are all symmetric matrices
Mm.
PSDs, or there is no rule like that?
No, no, no. There's no rule like that. Yeah. So
I see.
actually, you can construct some very simple examples where they start breaking this PSD rule. So yeah, so PSD matrix, the best way to understand that is using this sort of a rule. If you have a matrix, it has to be square, that is for sure.
Yeah.
Um, the thing that if x transpose ax for all x is greater than or equal to 0, only then it is PSD. Otherwise,
Correct.
it's not. That's the thought process.
Yeah. Fine. Fine. Yeah. Thanks.
Okay, right. Yeah. So coming to this idea of moment generating function. So again, this was something that I didn't, get chance to learn. So I'll just put a very simple sort of idea. Um, so let's say, x is some random variable which follows, let's say, a distribution called px, where x, let's say, will take for now scalar, and the fact that it is a absolutely continuous random variable. And let's say I have a variable called t, which is also a scalar. The moment generating function for this distribution is a function of this form. So where we take the expectation of this quantity called e power tx, t into x, over the distribution of x, right? And this from Lotus, we know it's just going to be an integral of this form, right? So when we extend this idea to multivariate distributions, we come to something like this. So we say again, let's say x is a random variable and it's a d-dimensional random variable. And let's say I have a variable called t, which is also a d-dimensional random variable. And let's say x is absolutely continuous. Then your moment generating function is defined as exponential over, expectation of e power t transpose x. Now, t transpose x is basically a scalar quantity, and therefore e power that scalar is well defined, and therefore this expectation, I mean, you can compute. And again, the expectation is over the random variable, which is x here. And from Lotus, we know that this ends up being can be computed in this form. Now there's an idea that the MGF and PDF for any random variable are equivalent. That is, let's say if I were to tell that, let's say that follows Gaussian distribution, let's say mu comma sigma, right? This is equivalent to saying that x follows, let's say, the MGF of whatever the distribution of the function is for this PDF function. All right. So m, let's say, for n of t, right? So basically, what this says is that if you want to characterize a random variable, obviously one way to do it is, giving the probability density function. The other way of doing it is basically giving the moment generating function. So therefore, any PDF, so any unique PDF will have a unique MGF and vice versa, right? So that is a very strong idea in probability theory. Now, why is that and all? I'm also a bit confused. So in case if I get more clarity, we can discuss some other time. So now we'll define the, we'll come to this idea of MGF for multivariate Gaussian distribution. So let's say X is a multivariate distribution. So we know what P of Px is, and we want to define the moment generating function of this variable X. So this can be seen as expectation over this function. So therefore, I can write this expectation of T transpose X into the probability density of the multivariate distribution, taking again very simple sort of idea from integration systems. So x minus mu is z, x can be taken as mu plus z. This ends up being something like this, where we have the expectation of T transpose mu on the outside, and I have a integral over expectation of T power z into this quantity with the the constant term carrying through, so on. And then, so here comes the idea. So let's say, for example, so now I need to compute this expectation, this integral, right? So what we do here is we say, let's say, so now we say that, let's say sigma t is equal to some variable called nu, right? So t can be seen as sigma inverse nu, because sigma is again invertible. We have assumed this for any non-degenerate multivariate Gaussian distribution. So so therefore, what it means is for every t, I'll have a unique nu, and for every nu, I have a unique t, right? Just because of the fact that sigma is invertible. So we can now look at this quantity, which is minus half z transpose sigma inverse z. And then I have t transpose z. So this t can be written as sigma inverse nu transpose z. And then I end up, solving this for a bit. So this sigma inverse nu transpose is nu transpose sigma inverse. Again, because sigma is symmetric, even its inverse is going to be symmetric. And then what we'll do is we'll do something called as complete the square, right? So if you think about it, this is the term that we have in the multivariate distribution. If you expand this term, we get something like this, right? So yeah, so we'll have a quadratic term in x, a linear term in x, and then a constant term. So we'll write it in the same form, and to get something like this. So we'll get minus half z minus nu transpose sigma inverse z minus nu, and some constant term which doesn't depend on z at all anymore, right? So this exponential term can be written as exponential of these two quantities, right? Again, multiplied. This can be taken outside as it doesn't depend on z, right? Now the remainder, that is this whole term, can now be seen as a Gaussian distribution over z with the mean parameter nu and the variance still being sigma, capital sigma. Now we know that this quantity is 1, right? So so I'm left with this expression, right? And now we already know that nu is, we have defined nu to be sigma t, and that you can again put it here, right, in this expression. So we'll get t transpose sigma inverse sigma t. Again, sigma inverse sigma is I, right? So this becomes t transpose sigma t. So I'll finally get a expression like this. Now, again, so the idea that why PDF and MGF are equivalent, as you can see, this function depends only on mu and sigma, right? One sort of intuition behind why that could be the case. So the Gaussian distribution needs two parameters, mu and sigma. Similarly, your MGF for the Gaussian distribution also needs the same parameters, mu and sigma. So if you know mu and sigma, this defines your MGF, which is equivalent to defining um, a PDF over a random variable, which has this form of multivariate Gaussian, right? Now, similar thought process you can do for the scalar Gaussian distribution, and it turns out to be again very simple T mu plus half T squared sigma squared, right? Um, so I did rush over the derivation. So again, just feel free to look through it, and if we have any doubts, we can discuss in the next class. Does that sound good?
Yeah, sounds good. It's only like some, like
Some
I'll try it out, no problem.
right,
I
yeah,
don't think there is much in it. Yeah.
right, yeah. Okay. With that, we'll look at some, thought this idea of multivariate Gaussian distribution. So first thing is something called the linear transformation theorem, which tells that let's say if X is a multivariate Gaussian distribution, and let's say,
So
yeah,
I'll just come in 30 seconds. Is that fine?
sure, no worries, yeah, yeah,
Okay. So I'll just come and ping you.
yeah,
Okay,
yeah,
30 seconds.
yeah, yeah.
Okay, I'm back.
Okay, yeah, we'll resume. Um, Yeah, so we were discussing about this thing called as linear transformation theorem for multivariate Gaussian distributions. So let's say I have a random variable x which follows n mu sigma, and I have another random variable, let's say y, which is a linear transformation on x. That is, we define y as ax plus b. Again, so a is some matrix and b is some vector. Um, so then what this theorem says is this y is also going to be a multivariate Gaussian with mean being a mu plus b and the variance being a sigma a transpose. So this and this I used to change the variance of compute the variance of y, right? So a very simple sort of thought process. So we'll start with this MGF idea. So let's say, so we know what the moment generating function of X is going to be. That is T transpose mu plus half T transpose sigma T. And then we'll look at the moment generating function of Y. And as we know that from the equivalence of moment generating functions and PDFs, if I get this moment generating function of Y in this form, right, then I can say that, okay, it's going to be some Gaussian distribution, right? With whatever respective parameters. So we'll look at the expectation over this quantity e power t transpose y. So this expectation here is with respect to y. Then I put this y as ax plus b. So now the random variable has changed to x. This expectation is now over x, right? T transpose ax plus b. Simple algebra shows us that we can take this e power t transpose b outside, and this becomes expectation over e power t transpose ax. Now, this can be seen as the moment generating function of x evaluated at this quantity called A transpose t. So we can write T transpose AX as A transpose T transpose X. So this is going to be a vector that, so I'll basically have to evaluate the moment generating function of X at this vector called A transpose T. So that ends up being exponential of, again, just put the value in the MGF of X. It turns out to be something like this, right? And then I can, now both these are exponentials, just add up. So we'll get exponential of t transpose a mu plus b, right? And then this remains unchanged. And here we can see that this is the quantity that's coming between the t transpose and t. So therefore, this becomes the mean parameter of the random variable y. This becomes the variance parameter because this is of the form of Gaussian distribution, right? So this is a simple idea again from the thought process of MGF functions. Now, what implications does this have? Where do we want to use this idea of linear transformations theorems? So first thing is that we can look at it from this perspective. Let's say if I have a random vector, again x, from x1 to xd, d-dimensional random vector. If x is a multivariate Gaussian distribution, then any linear combination of the random variables x1 to xd actually follows a Gaussian distribution in itself. So we're saying that, let's say if I have x1 to xd, I take a linear combination of x1 to xd, where a1 to ad, the coefficients are all real numbers, all possible real numbers. Then this is going to follow a Gaussian distribution with some mean and variance with some mean and variance. Now we need to understand here that y is not a random vector anymore, right? Because all of these x1 to xt are scalars. You're taking a linear combination of scalars, so this is going to be a scalar. It's just going to belong to the real number line. So this is a univariate Gaussian distribution. So very simple thought process. I can just say let A in the previous theorem be just A1 to AD, some vector. Let's 1 cross D matrix, and then Y becomes AX. So and let Y be AX. So this becomes just exactly what we have here in place. So then we know that Y becomes a Gaussian distribution with mean A mu and variance A sigma A transpose. A mu becomes, again, very simple, just the linear combination of the means, and variance becomes A transpose sigma A transpose, which is basically can be computed in this form, right? Each element of the variance covariance matrix multiplied by the respective elements of this linear combination coefficients, right? The It's also possible to prove the other way around. So what does the other way around actually mean? Let's think about that. So what we're saying is that, let's say that there's a random variable, let's say y, which I get from some random variables x1 to xd, right? So our claim here is that I have some random variables x1 to xt. I don't know what their form is. I don't know, are they multivariate Gaussian distribution and so on. But what I can say is that, let's say if I take a linear combination of them, right? Some linear combination. This linear combination random variable will be a Gaussian distribution with some mean and variance, and it is a Gaussian distribution for any possible linear combination, right? So A1 to AD belonging to RD. So any possible values you take for all, right? This turns out to be a Gaussian distribution. So if this happens, right? If this happens, then what claim I make is that these x1 to xd, they are actually from a multivariate Gaussian distribution. That's the reverse part of the implication, what it means, right? So to prove that, we can go ahead and look at this, what's it called, MGF of the random vector x, right? At t. So if we can prove that the MGF of,
Just like
yeah,
I want to clarify, like so that we are on the same page. So you are
right.
saying if x1 to xd are random variables distributed following a normal distribution, is that what you are saying? Then the y would be a normal distribution,
So yes, so that was the claim in the first part. So
right?
this implication claim, right? So in the
Yeah,
forward claim was this.
fine,
Yes. So, the reverse claim is that I don't know what x, this random vector x distribution is, but
right?
if they satisfy this property such that any linear combination of them is going to be some Gaussian distribution,
I
then
see. Okay,
I can say that x1 to xt actually follow a multivariate normal distribution.
okay, understood. Yeah, thanks.
So a priori in this, in the reverse implication, a priori we don't know the distribution of x1, xd, or their, their joint distribution. Nothing we know, right?
Hmm.
What we know is that the linear combination will be a Gaussian for all possible linear combinations.
Yeah, yeah, fine. Uh, so intuitively, like I want to understand this.
Ah,
Uh, so for example, like we took some examples in which we were dealing with mixture of Gaussians.
right.
So for example, like x1 is a Gaussian random variable having some mean and some variance, and x2 has some other mean, some other variance. Let us say that. Then
Hmm.
y would be a mixture of Gaussians rather than Gaussian. Is that correct?
So why see? So mixture of coefficients is a stronger statement because there your mixture coefficients have to sum to one. They have to be greater than zero. All of that,
Okay, fine.
right?
Hmm.
So in that case, if you think about it, so and um, 1 second. No, no, no. No, no. Okay, this is where things get interesting. Okay, in GMM, what are we doing, right? In GMM, the probability density is a mixture, right? So this is what it is.
Right. Correct.
Okay. So here,
You're only summing the random variables there. Here.
in GMM, we are adding up, we are taking a convex combination of the probability densities.
Right.
That is a GMM. Here we're adding actually the random variables themselves.
Right. Right. Okay. Understood.
Huh.
So it will okay. Intuitively also it will be a Gaussian. So I think like it will be Gaussian for Gaussian irrespective of the distribution of x. Is that also correct?
Uh, uh, which one? You're saying why? This
Yeah, yeah,
particular.
yeah. So I'm saying
Hmm.
this equation. So y
Uh,
will follow a normal distribution
uh,
irrespective of the distribution of x. X can be exponential. X can be uniform.
correct, correct. So let's say I have a set of random variables, let's say x1 to xd, for example, right?
Hmm.
It is possible that there'll be some linear combination that I can take of these, such that I get a Gaussian distribution, right? Now the claim here is for all possible linear combinations, if this happens,
Understood. So yeah, yeah.
uh,
Then each yeah, 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 fine.
right? Then we can say for a fact that x1 to xd are actually a multivariate Gaussian distribution.
Yeah, yeah. Hmm.
So that's the thing. Now, so one example in this thing if we want to think about is, let's say for example x1 is, for example, let's say some exponential, x2 is, for example, let's say exponential plus Gaussian, right? Then if I just take simply x2 minus x1, right? So y is going to be a Gaussian distribution, right? Again, you can prove all this very simply, but
Hmm.
is this so? But for every possible linear combination, no. That's not going to happen. So hence, this is one counter example where they can have different distributions. You will have, let's say, some possible combination. I mean, there could be possibility that there is some linear combination where it turns out to be Gaussian. But the fact that if what we are making a stronger statement is that for all possible linear combinations, this should happen.
Right, right. So it's clear now.
Yeah. Okay, good. So that's the thought process. Yeah. So then, how do we go about proving something like this, right? So one again simple idea which we just dealt with was that if we can prove that the MGF of this random vector. So now let's say x1 to xd is a random vector I can consider, right? So if I can prove that the MGF of the random vector follows this form that we have discovered today. So if it follows this form, then I can say that yes, X will be a multivariate Gaussian distribution. So for that, we can look at expectation of e power t transpose x. This is the definition of mx of t. Now, what I will do is t transpose x basically can be seen as just the linear combination of each of these random variables, right? So this, let's say I define it to be, let's say y. Now I know that for any possible t, this is going to be a Gaussian distribution. So if so t transpose x, so it becomes y. So y is now a Gaussian distribution from the premise of the statement, and this we know the MGF of y so this is MGF of y at t equal to 1, right? It is 1 into y. So I can write it as exponential of mu y plus half sigma y squared from the MGF of univariate Gaussian distribution. Now what I need to do is I just need to find out what mu y and sigma squared y are going to be. So mu y again very simply can be seen as the exponential of, expectation of t transpose x, which is just going to be expectation over the summation of this random variables. Again, from using the idea of linearity of expectation, I can break this down into um, this idea that sigma I ti mu I. Now this sigma ti mu I can be seen as t transpose mu, right? So one part is sort of very clear, and there's one thing that we need to think about here is that these we're making two assumptions here. One assumption is that each expectation of xi exists, right? And this is not a bad assumption to make. Actually, not even an assumption, because of the fact that we just said that y is going to be y is going to be a Gaussian distribution, right? So if I take, let's say, for example, a1 to be 1 and remaining all elements to be 0, right? What will happen to y, right? So y will just become x1, right? So now we know for a fact that x1 is going to be a Gaussian distribution with mean mu and sigma square, some sigma squared variance, some this one, right? So expectation of x1 exists, which is mu y, and variance of x1 also exists, which is sigma squared y. So these two conditions, so variance of xi also exists. And what does exists mean? That is not equal to infinity, or doesn't blow up to infinity or minus infinity, right? So therefore, this linearity of expectation, can be applied in this scenario, and then we get this T transpose of mu, right? This linearity of expectation internally has these sort of assumptions, right? That the variance, expectation should be existing for all internal components and so on. Now, to come to the variance of y, this is going to be a bit of a hassle. So for that, we'll require some basic ideas. Again, just a brush up of what we do in random variables. So yeah, so basically, let's say if I have two random variables, let's say x and y, the variance of their sum can be seen by definition in this form. That is expectation of x plus y squared minus expectation of x plus y, the whole square. This, by the way, is expectation over the joint distribution of xy. This is also over the joint distribution of xy. I can then break this down into these terms. And this can be again looked at as expectation of x plus expectation of y whole square. Again, break it down into terms like this. So this turns out to be expectation of x squared minus expectation of x squared plus expectation of y squared minus expectation of y whole square, and then plus 2 times expectation of xy minus expectation of x and expectation of y, right? So what we do is we define this term as the covariance between x and y. This is just the variance of y. This is just the variance of x, right? So this is for variance of a sum of two random variables. Again, very simply, we can show that variance of ax is equal to a squared times the variance of x. We'll use all of these identities going forward. It is proof. Um, Covariance of x plus y is as we defined just above. So what is the covariance of x plus y comma z? This again can be seen very simply. X plus y into z minus expectation of x plus y into expectation of z, right? So this turns out to be expectation of xz plus yz minus expectation of x into expectation of y, sorry, plus into expectation of z, right? And this turns out to be basically covariance of xz plus covariance of yz, right? So covariance basically is a linear sort of an operator. So if I have two or three more, two or three variables in this form, I can just add up their covariances. And what is the covariance of ax comma by? So if I scale a and b variables x and y in some way, how does the covariance change? Again, very cleanly, this can be seen as from the definition itself. Um, Expectation of by, this will turn out to be ab times the covariance of x comma y, right? So covariance is again a scalar, I mean linear in this form also, that if I scale it up, I'm going to get just a scalar multiple of the same covariance, right? So with this in hand, we can look at the variance of these summation of d random variables actually, right? So what I can do is I can break this down into two random variables. One is a summation until d minus 1, summation, and the last term, let's say d xt. Now I can apply this formula, variance of x plus y. So this is one random variable, let's say a, variance another random variable, let's say b. So it's because variance of a plus variance of b. Variance of b is td squared times the variance of xt plus 2 times the covariance of these two random variables. So I have covariance of a random variable, let's say a and b here. Variance of xd will give a notation called sigma dd, capital sigma dd, and we know the covariance is linear, so I can just write it as sigma I equal to 1 to d minus 1 covariance of tixi comma tdxt. We know that this term is basically going to be ti times td times sigma id, right, with 2 in between. So this, in this way you can continue. I have not completed the proof right here. Let's try proving this. Ideally, what should happen? What should you expect out of this is basically some form like this, right? Because this is exactly what you want at the end of the day. So if you're able to mention, if you're able to show this the sigma square to be a sigma a transpose sort of a method, sorry, t transpose sigma t sort of a expression. So that will turn out, that will make sure that will prove that x turns out to be a multivariate Gaussian distribution, right? So we've already shown mu y is t transpose mu. Sigma y squared can be shown as t transpose sigma t. This basically what you need to show is something like this: ti tj sigma ij, right? So you form sigma matrix such that sigma ij are its elements at ijth location. Then you'll end up proving that x follows a multivariate Gaussian distribution. Okay, fine. So I'll leave it for now here, and then we'll see how. I mean, we'll see the next class we'll complete this proof also. Now, the application of this is very interesting. So one application here, what we will end up doing is, sorry, one application for this is um, the idea of let's say if I have uh, uh, a, a multivariate Gaussian distribution, n of mu sigma, we can show that each component is actually a Gaussian distribution in itself with mean mu I and the variance sigma I squared, where sigma I squared is just the ith element of this one. Also, additionally, what we can show, again using this thought process, is that x, so let's say if I have any set of any subset of these random variables, x, right? Let's say x is x1 to xd, right? If I choose, let's say, some subset of x, let's say xs to be xi, xj, xk, or whatever subset you want, this can also be shown to be a multivariate Gaussian distribution, right? With mean mu I, mu j, mu k. And the variance matrix is going to come out very, very cleanly to be sigma I squared, sigma ij, sigma ik, and so on, right? So basically, whatever sigma matrix you had, just cut those parts which correspond to xi, xj, xk. That will become the variance of this variance covariance matrix for this new multivariate distribution, right? So all of these nice properties of multivariate distribution, and all of these will basically end up using to make a life much more easier when we deal with VAs. Now, one last sort of idea from multivariate distributions is the idea that, let's say, if I have x being a multivariate distribution, if sigma ij is 0, that is, if the covariance of two of these random vectors is 0, then we can prove that xi and xj are actually independent. Now, the reverse implication we already know. That's obviously a thing that we have in mind. Can be proven using the covariance definition. So sigma ij is basically the covariance. And if xi xj are independent, we know that this holds true. So the expectation of the product is equal to the product of the expectations. So this ends up making your covariance to be 0. The other way, if you want to prove, which is not generally true, but true for multivariate Gaussian distributions, which is exactly what's make them so much interesting, is that, again, how do you go ahead and prove it? Let's say if I make a matrix called A, which is a 2 cross D matrix, such that all the elements of the first row are 0 except the ith column, and all the elements of the second row are 0 except the jth column, right? And I define now Y to be AX, right? So A is a matrix, it's a 2 cross D matrix, and X is a random vector, which is, let's say, D cross 1. So Y is now going to be a bivariate, bivariate Gaussian distribution. By Gaussian because, again, it's a linear combination of x. So it becomes the mean is a mu and the variance is a sigma a transpose. That can be used to understand what. So what is y? Basically, y is going to be y is going to be the variables xi and xj, by the way, right? Because that's yx from here. A mu is going to be mu I mu j. Again, very simple thought process. A sigma A transpose. This you can look at the math. I won't do the in verbally here, but the idea is that this will turn out to be exactly the variance covariance matrix of containing I and jth parts, right? Now we know from the statement that sigma ij is 0. That is, let's say, the variance, the covariance between I and j is 0. So the variance covariance matrix of your xi xj, that is y, is just going to be sigma I square, the variance of ith component, and jth component with of diagonals being 0. So your xi actually follows a multivariate distribution with mu I mu j, and this as a variance variance covariance matrix. So then we'll use the definition of multivariate distribution. So what is the determinant of sigma y is basically sigma I squared sigma j squared. The inverse is 1 by sigma I squared 0 0 1 by sigma j squared. We'll now look at the look at this term in the multivariate distribution formula. So this turns out to be xi minus mu I times squared by sigma I squared plus xi minus mu j squared by sigma j squared. What we need to prove for independence, right? We need to prove that the probability, the joint probability distribution of xi xj is basically equal to the probability, the product of the probabilities, right? If this happens, then this is by definition the fact that xi and xj are independent, right? So for that, we look at the joint distribution, which we proved is exponential multivariate with these mean and variance parameters. So that can be now be broken down into two parts exactly, right? So I have 2 pi power half sigma I here, exponential of this term, 2 pi power half sigma j exponential of this term. So this is the term which contains exactly only the components of xith element of the random vector and xjth element of the random vector. This is basically the marginal of xi and xj. So we have now proven that xi xj joint distribution is equal to the multiplication of their respective marginals. So therefore xi and xj are independent. So this property holds only and only for one of the special properties that special distributions that follow this property, that if the covariance is zero, the terms end up being independent. Now, with this in mind, again, any doubts here? Again, this is all just basic math. Go through it in case this is not clear, right?
Yeah, it's clear. It's clear.
Okay, so with that, we'll go into how this helps us in the VAE formulation. So the first thing, so the implications, we come back to the implications of sigma phi. So sigma phi, we said we'll take it as a diagonal matrix, and that means basically all the non-diagonals are zeros. So what this would mean for the random vector z, um, very simply, what that means is we are looking at z as a, let's say, a random vector z1 to zr, such that each of these components or each of these latents components are basically independent of each other, right? This is the implication that we have here, right? So so we are looking at the z as a random vector which has independent components in itself, right? That is one implication. The other implication, operational implication, we'll discuss when we discuss sampling. All right. So hopefully this is clear. This is the idea of why how taking it as a diagonal matrix helps. All right. Now we'll look at how we can actually compute these two terms that we have in place, right? So one was this. How do I? Yeah. So we have two terms in this elbow, right? Which is basically we have an expectation over q of z given x, and I have a KL term, right? So how do we compute this KL term? Any thoughts? You already discussed the respective math behind it. So we have the KL between, to be very precise, is exactly what we are trying to do, right? So any thoughts?
Regarding what?
So how would you compute the scale term in elbow? At the end, you want to compute them so that we can get gradients, etc., etc.
So, uh, do we? So we right now don't know phi. Okay.
Right?
So we need to first find out phi to compute these terms. Is that correct?
Correct. So, and as you know, in any neural networks, the idea is that you start with some parameters, right? You start with
So
some.
okay, fine, yeah. So like yeah. So in the first iteration, I will be able to compute this
Correct.
scale divergence. Yeah.
Yes. Yeah. So, but how would you go about doing this? So, if you have to compute the scale difference, how would you go about doing this?
So I know phi, therefore I will know mu phi x and sigma phi x.
Mm.
And once I know these two things, I will like use the formulas that we discussed like some time back to compute the scale divergence, and that would be a function of that would be a function of okay,
Ah.
maybe you have to go ahead.
Yeah, yeah. So basically, yeah. So we discussed one formula, right,
Yeah,
before, as you mentioned, right? So the KL between two Gaussians, right? Because again, as simple, these two are Gaussian distributions, and we have already discussed how to compute the KL difference
scale
between
divergence.
Gaussians. You know, in a closed form sort of a solution.
Right, correct.
Yeah, so let's invoke that and we'll see, so we'll see what the final term it comes out to be. So where did we do that? KL divergence. Yeah, this is the one that we have. So let me just see if I can copy this. Can see. Great. So yeah, let's just. So this is the formula that we have, right? That we discussed before. Um, so now, if I have to compute the KL divergence, so what will end up happening is I need so KL divergence of this Q phi is going to be half of log of sigma Q, right? Sigma Q is sigma phi of x, right? It's determinant we want divided by sigma p determinant. Sigma p is, oh sorry, my mistake. Yeah. Oh, so PQ is reverse. So, okay, so the second distribution, yeah. So log of sigma Q. So in this case, it is a determinant of I, which is just 1, divided by, I want determinant of sigma phi of x, right? Minus, let's say, d by 2, plus half of trace of sigma Q inverse. Sigma Q is I here, I inverse is I into sigma P I will get, which is that is sigma phi of x, right? So trace of this matrix plus half of their mean differences, right? So mean of this minus mean of this. So mu phi of x minus zeros is just mu phi of x. Sigma Q uh, inverse is just I, right? I inverse into again say mu phi of x, right? Mu phi of x, right? Okay. So so as you said, how we determine this sigma phi is basically because it's a diagonal matrix, and we will just output from the neural network the diagonal values only, right? So for brevity's sake, what I will write is I will write this as something called as a diag of sigma phi, right? Small sigma. This is basically a vector, right? Which gives me the the variances of individual components, right? Variance of individual components again as a function of x, right? And obviously as a function of sigma r squared of x as a function of phi, right? So I have a phi somewhere here, phi, and phi, right? So diag would mean just put all of these values in the diagonal and remaining everything is 0. So therefore, this half log or whatever, so this minus half, I can take this, and the determinant will just basically be the product of these elements, right? So product pi equal to pi 1 to r, sigma squared, or whatever the output of neural network is for that particular dimension of x, right? So minus d by 2 plus trace is going to be just the summation of these components, right? I equal to 1 to r, sigma squared phi I of x, plus, now this is basically mu phi of x, I inverse mu phi of x. This term is basically just going to be mu phi of x squared, right? So it's just the this again can be seen as whatever dimensions of mu phi are, we're just multiplying them with each other, right? This is transpose here, yeah. So yeah, so we'll have mu phi of, let's say, the ith dimension, take the summation, right? So this is going to be I equal to 1 to r mu phi ith dimension of square of x, right? Again, as we expected or as we want, this is a function of x, right? And depends on phi. So whatever gradients that you want to, compute, now you can compute them very easily. One small operational point is that it doesn't make sense to include d by 2 anywhere because it's a constant, and any gradient operation will just uh, make it to 0. So we don't care about this d by 2 term anywhere. We just care about the terms which involve x and phi, right? So again, so this is one way of doing it. Another operational sort of thing, what people do, or what people end up doing, is they predict, instead of outputting the value sigma squared of phi or whatever, what they output from the network is basically log sigma, right? Log sigma. This is taken as the output of the network, right? On this, what they do is they apply e power, as we discussed, right? So let's say I'll call this as um, let's say VI. Okay, so the variance of the ith component, I mean, the predicted value is log sigma. So the variance, that is sigma, whatever you want, sigma phi of I, sigma phi I of x is taken as e power vi. And that's how they put those terms here, and you will be able to compute this value in closed form, right? So this is obviously, one way of going about it, and this is exactly why we discussed this KL difference between two Gaussians, and we were able to get a closed form solution. So now I can easily get gradients with respect to phi for the DKL term, right? Right. So this is one idea. This is one thought process. Another thought process. So there's one more way of computing any general KL. So from the definition of KL itself, any thoughts on, can we use that here? So just to put things in perspective, let me just put down the KL divergence between, let's say, P and Q can be seen as an expectation over P of the quantity log P by Q, right? So any thoughts, like if you didn't have this closed form solution, beforehand, so what would you do if you have to compute this expectation? Any thoughts?
So compute this empirically.
Compute empirically, and for that, so how would you, yes, so how would you go about doing that then? For this particular scenario, I mean, for this particular scenario where I have q phi of z given x and p of z.
So compute the expectation you have, like you have many samples to train your data on, and using that you compute the expectation of these two terms, and
Right,
then yeah.
right. So you will take, let's say, take let's not use capital N. So let's say I'll take capital L number of terms, right? So L equal to 1 to capital L, and you're saying I will do something like log of P of z L, and P of ZL is basically this P of Z, and Q phi of ZL given X. And how would you get these samples?
And L is the number of samples. Is that correct?
Correct. L is the number of samples. Yep.
Okay. So I'm using like some samples to compute this expectation. Fine.
Yes.
So now what's the question? Could you please repeat?
So how would you get these samples though? Like, so we want to approximate the expectation using samples, and that's a good thing, I mean, valid thing to do from law of large numbers. We know all of that. Now the
Right.
idea is you want samples. So how would you get those samples? What will you sample to get these ZLs? What distribution will you sample?
For each training sample of the for each X in the training sample, I'll get some output. I'll
Right.
consider that as ZL.
That is ZL, is it?
Yeah.
So but the output is not a ZL, right? Though, right? Output is what from the network, from phi network.
Okay. So output is okay. Okay. Correct. Correct. So output is those R values of mean and R values of uh, variances. That's it.
Right.
So
Huh.
ZL is not the output. Correct.
Huh. So ZL will basically be samples from this distribution, right?
Oh, okay. Okay. Makes sense. Yeah. Yeah. Correct.
Huh. So we'll use this X to get the mean vector of this Z vector, and to get the variance covariance matrix. Use these to get samples from Z. That's the idea.
Yeah. Understood.
Okay, good enough. And then another sort of thought process that we can think about is that now we don't need to actually do a multivariate sort of a sampling, because of the fact that we have assumed sigma phi to be a diagonal matrix. So we know for a fact that each dimension of Z is independent of each other, right? So another one thought process could be that I sample each dimension separately. Let's say I mean, ZL1 to ZLR, right? So this is basically the R dimensions of the Lth sample, right? And each ZLI here, basically the Lth sample for ith dimension, can be seen as a Gaussian distribution over, let's say, Zi, the ith component of the Z random vector, which is the scalar random variable. The mean is mu phi of I comma x, the ith output, and the variance that we already have in place
Yeah.
as the output. So this is the way you will operationalize computing this particular KL term, right?
Yeah. Yeah. Correct.
Right. So now, okay, we discussed two ways. Which way would you prefer? Any thoughts? One versus two, which is something that you would prefer?
Can I see version one because I
Hmm. So this is the version. Yeah. Hmm.
so here the neural network is outputting those R values directly, and using that we are computing the this
Hmm. Right.
so in the second method,
Hmm.
for each sample I am getting. Okay. So could you please again summarize the difference between these two methods? Like I'm finding them to be like quite similar. So
Huh. Okay. Yeah. So the point here is that we want to compute a scale term. Now, there
Right.
are two ways to compute the scale term. One way, what we have the first way we have discussed is we have looked at directly as a functions of the input itself. And what the neural network outputs, right?
Right.
So we have
Right.
basically computed this in a closed form in some sense,
Okay. Fine.
right? So if I have to take, let's say, gradients of this term, I can, because I have it in this form, I can keep on applying, let's say, product rule or whatever rules apply for, this gradient, and keep getting the gradients and basically back propagate all the errors and stuff. Second
Yeah.
is basically I don't use a closed form solution. I use the actual the Monte Carlo estimate sort of for computing this expectation with these values that I have in place, because I can always calculate Q phi of Z given ZL given X. I can always calculate P of ZL because I know what those distributions are, right? And then compute some value and then go ahead and hopefully in some way back propagate the errors, gradients.
Mm.
So given so these two, what would you generally prefer? Again, this is actually more a question of uh, general thought,
Implementation.
hmm, implementation and yeah, general thought process. So how would you like when would you prefer something like this over this, or versus, let's say, two versus one?
Okay. So in all practical cases where maybe the data is limited,
Hmm.
I'll implement version 2, like second method,
Okay.
or maybe like only in very specific cases where I have like lot of data, I'll try with version 1. Is that correct?
Okay, so you said version 2 for limited data,
Limited data.
right? Limited data in what sense? Limited samples, you mean, right?
I mean limited samples, correct.
Limited samples. Okay, but are we dealing with limited samples in this particular expectation though? So what are we computing the scale for? We're computing for one sample. We have not even gone to multiple samples, by the way, till now, right?
Okay, right.
Huh.
So if we are computing it for one particular sample, then this particular estimate may be noisy.
Okay, yes. Mhm. Compared to this closed form
Yeah,
solution in some sense.
yeah, yeah.
Right? Correct. So
Right,
yes. So 2 basically has the noise, the variance in its estimates that will come up into place. Variance in
and
estimates
in the first case, given that we are taking an expectation over all possible samples, the amount of noise would be reduced.
would be reduced. Right. So first thing is, yeah. So we have variance in estimates. That's basically the whole idea of your law. I mean Monte Carlo estimates, right? So they will be noisy. Now, and in more general, when would you use? So let's say I have an expectation of some quantity, right? Some f of x. There are two ways to compute this. One is take Monte Carlo estimates. Another one is, can you get in a closed form, right? So if you're able to get in the closed form, ideally what Monte Carlo is trying to do is trying to reach the closed form, right?
Right,
If you
correct.
have closed form, just go ahead and use it, right? In case you
Right,
don't have the closed form solution, which is exactly what the problem we have in the initial sort of a problem statement, right? Because we don't have the px distribution that we want. If we had that, life would have been much easier. So since we don't have, we are doing all of this stuff to get. We take Monte Carlo estimates, assuming that the samples are whatever data we have are samples from the original distribution, right?
right,
So yes, we'll end up using the closed form solution with blindly, just because we're able to compute it. All
right.
right. Okay. So hence, I mean, so you see now the fact that we got closed form was because of these assumptions also.
Right,
That's that we need to keep in mind, because we assume this to be a multivariate distribution. This also was assumed to be multivariate Gaussian distribution. We could compute a closed form, and that closed form is what we'll use to back propagate the errors when you come to the KL term optimization. All right. Uh,
yes.
Good. So this is the part of the KL term. Now let's look at the first term that we have in place. So I'm calling it reconstruction term, and there's a reason for that. So what we have is we have a term which goes like this: z given x log p theta of x given z, right? So now, yeah. So now, why are we calling this reconstruction term in this elbow? Is basically, if you see, uh, again, we are trying to maximize f theta, right? Maximizing f theta would mean I have to maximize this also and reduce the KL term, by the way, right? So this will so if we just look at the term here, so maximizing this means I have to maximize this and or minimize the KL, right? This is the idea. So because of negative sign. So now here, if it's I'm trying to maximize this quantity, right? I'm trying to maximize this quantity. Now here the idea is, let's say, so for a given x, as we saw, q phi of z given x is a distribution over the latent variables latent variable z, right? Now what are we trying to do is we are trying to look at the expectation of p theta of x given z. So p theta of x given z is another network, right? Which we haven't discussed till now, but this is what we need to see. Theta is a network again. We said that we are going to model p theta of z given x also as a neural network with parameters theta, right? So what is this neural network trying to do? It's going to take z as input, right? And output, let's say x, right? Or and once you have x, p theta of x, p theta of x given z is something that you have in hand because you know what the model that you have with you, right? Again, we'll discuss some assumptions under this also going forward. But let's say we assume some form for p theta of x given z. So if the network outputs a value, a variable in RD space, which is x, I can always compute this log p theta of x given z. So the idea is that I am trying to reconstruct the value x back, right? So I'm taking x, I get a distribution over z. I take, let's say, samples from this distribution z because that's one way to compute this expectation, right? So I'll take samples over this particular distribution over z and then compute then get, let's say, some x. So the idea is that I want to get the same x from the same from this x again, right? So basically, we're trying to reconstruct what x was there as an input back as the output of this network called theta, right? So this is what the reconstruction term is trying to do in the elbow, right? So maximizing this means we're trying to get that x back. So if I have an x, I get a distribution over z, take the distribution, get x back, right, from this network theta. So this is the idea of reconstruction term. Any doubts or questions here?
No, it's fine. Clear.
Right, right. So with this in mind, so then we asked the question, what exactly Z is doing, or at least supposed to do? We answered this question in the GMM example that we discussed in the last class. Was that we said in GMM example where we had cats and dogs, we said Z is basically capturing the what type of image it is, right? What type it is, one or two, basically cat or dog, right? So here, what Z is doing? Any thoughts from this discussion that we had?
So Z is trying to capture all that information which is essential to reconstruct X.
Right. Hannah. So this is where we come up with the question of relevance, right?
Right.
So,
Right.
right. So this is where we say that, okay, so Z should, I'll put should in quotes, should capture all information about X to reconstruct it, Basically, it should be able to encode X in some probability space, right? And why I'm saying probability space is because Z as such is a random variable, right? It's not a deterministic quantity anymore. So given an X, right, the distribution over Z given X, that distribution should be able to capture all the information about X that we have. So this gets mapped to a distribution. That distribution should be able to give me X back, right? This is known for a given sample X. For a given sample, we're trying to run this particular algorithm for now. So I have X with me. That X gets encoded into this Z space, which has some inherent probability or inherent randomness in it. But using that randomness or using that inherent information, we should be able to construct X back, that same X. This is what Z is trying to do, right? So any doubts or thoughts here, you can ask.
So
Yeah,
then this becomes very similar to PCA, because in Z also we are assuming that like the different dimensions are independent, which also
right.
happens in PCA. Just that like it's not probabilistic in PCA.
Correct. Hmm. Yeah, yeah, correct. It's not probabilistic in PCA. Another another point in PCA is it's some sort of a linear sort of a mapping,
Right, right,
right? That sort of idea actually moves on to this idea of autoencoders, right? So we'll discuss a bit about what autoencoders generally are. So autoencoders basically they are some sort of a neural network, right? Where the idea is basically, let's say I have some X. I'll map it. I'll have a part of the network called encoder. Again, this part is basically just what we define. The training is seamless. And then we have something called as a decoder, which is supposed to generate the same X back, right? And the idea is that we are trying to compress this X into a smaller dimension, right? So let's say some output, let's say Z. Now in PCA, the idea is this encoder decoder is basically a linear mapping. So here we allow the network to be able to discover any nonlinear mapping sort of,
mapping also. Mhm.
right, between the data and some latent variable called some variable Z, which is a compressed representation of X. That is the idea, right? So X prime
Right.
should be close to X, and then you'll look at let's say this becomes a loss, how different X prime is from X, and you train the network in that way. So one basic idea here is that Z is generally kept to be a low dimensional quantity compared to X's dimension.
Mhm.
Now that is because from the fact that you're of the manifold hypothesis that we discussed, right? The
Yeah.
idea of this manifold hypothesis, because we say that, let's say X is, for example, an image, right? Which lies, for example, let's say in 512 cross 512 cross 3 dimension space. The idea is that we don't need all of these dimensions. Again, don't need in the sense, the point is that many of these dimensions are correlated, or correlated, or let's say dependent in some sense, right? They are not independent. So we have a lot of redundant information in X, so we don't need all of these dimensions. Rather, if you're able to look at some independent dimensions of X, along which if we change something, we get different features of X. For example, let's say I can have face as one. Okay. So let's say we're looking at, let's say, dogs, for example. Breeds could be one dimension. The color of their fur could be one dimension, and so on and so forth. So if you're able to if you're able to get to those dimensions which are actually independent of each other, right? And so then we'll be able to capture all the information about X in these low dimensional space. That is again a result of the manifold hypothesis, right? This is the thought process. And this idea is what gave way to thinking about this variance matrix, that is this covariance matrix, uh, to be a diagonal matrix, right? So we want to basically, again, let's just go down, we'll keep all these things in together. So one is relevance. The other idea here that comes about is the fact that we want to capture variations, or basically factors which are which vary independently of each other, right? Independently of each other, and are able to capture everything about X, right? And this again is basically what you can say, uh, motivated from the idea of manifold hypothesis, right? And because of these reasons, why this is why we call this as variational autoencoder. So autoencoder part is because we're trying to go from, let's say, the same sort of a thought process. We have an X, we go to Z, we go to some lower dimensional space, and then we come back to the original sample X, right? But it is not exactly a deterministic low dimensional representation. Rather, it has some sort of a probabilistic thought process, and that is why we call variational, because of the variational connect that we had before, where we are trying to look at this as a random variable, and we're trying to minimize the KL between the latent posterior and the approximate posterior, right? So that's the reason of calling it variational, and calling it autoencoder is because we're trying to get back the same quantity from this intermediate representation, which is ideally low dimensional and probabilistic in nature. All right. Okay. So any questions or thoughts until now?
No questions.
Okay. Okay. Good. So yeah, so I guess so this is where we'll end today's class. Next class will look at something called as reparametrization trick. Again, I would suggest just go through the paper, the original VAE paper. There they represent this idea, reparametrization trick. Now, one would think, what else is left, right? I mean,
Right.
so we can compute this term. I'll take samples over this Q5, right? I have a closed form solution for the DKL term, that too with all the nice things. It depends on X, it depends on phi. I can take the gradient, everything, etc. One thing that we have slightly sort of not touched is this, right? I'll put it in red. So let's say, so how do I take the gradient of this term, right? That is what is pending, right? Um, if, for example, I would compute this term as an using a Monte Carlo estimate, right? Um, so think about how to take a gradient with respect to phi and with respect to theta, by the way, because this term involves theta also. KL divergence term didn't involve theta, so gradient with respect to theta is 0 for this term. We only have theta coming up here, so gradient with respect to theta also we will need. So we need this quantity, right? So if I were to take Monte Carlo estimate, what would happen to the gradient? Can we compute it in the first place? And if we can't, then what to do? And that's where the solution came about, using reparameterization. And we will use the ideas that we learned for multivariate normal distribution here. And we'll also discuss some strategies on sampling. How do you then do sampling? Because at the end of the day, we'll have to solve it using sampling, and we'll discuss why also. And that's what we will that will complete the idea of this whole discussion on VAs. All right. Okay, so any more questions? Otherwise we'll close the class.
Sounds good actually. I don't have any questions.
Okay. Good. So we'll close the class. So I'll see you next Saturday. Yeah.
Yeah, yeah,
Okay.
sure.
Bye.
Thank you.
Yeah. Yeah.